All right, here is an open-ended synthesis problem that, as you might have found from the title of the video, may involve carboxylic acid derivatives. We can see this aromatic ring has a para-substitution pattern. We know how to do that based on earlier semester topics. We also know how to install a carbonyl right next to the ring using an acid chloride. So perhaps this bond here could be one of our late-stage bond forming, giving us mainly the entire structure here. We also recognize that if we're going to form this bond, we have this whole piece to add, and we're going to need to have a bromine on one end of the molecule and a carbonyl on the other end of the molecule. Let's just refresh our memory about the rules here. We can use benzene, and we can use alcohols that have between 1 and 5 carbons. So if we want to bring in some extra carbons, we need to start with an alcohol that has between 1 and 5 carbons. That means if you want an alcohol that has 6 carbons, you need to make it first from smaller alcohols. So let's think about this. What if my last step here, or my almost last step, was T-butylbenzene plus the acid chloride of this right half of this molecule. I could use aluminum trichloride to react this. However, I think the aluminum trichloride might be interfered with by this bromine. So what if this were a protected alcohol? I could then do my aluminum trichloride acylation, and then I could deprotect the alcohol and turn it into a bromine, and I would be all set. So I think that's a good synthetic target here. I can make, let's see here, I can make this compound, of course, from benzene and T-butyl chloride, and of course I can make T-butyl chloride from the 4-carbon alcohol, so that's a good starting material. So I can start with benzene, I can start with T-butanol. Now the question is, how do I make this other more complex piece? Well, I can make the acid chloride from the appropriate carboxylic acid. Now I have a couple of options to make this carboxylic acid. Of course, we know that a carboxylic acid could come from a primary alcohol right here, or using a Baeyer-Villiger reaction, it could come from an aldehyde at the same position. So I'm going to think about both of those, but I'm actually leaning towards the aldehyde because in order to make a primary alcohol here, I probably will have to protect it at some point in order to make this CC bond earlier in the synthesis. And if I protect a primary alcohol and my secondary alcohol, it's going to be very hard to selectively deprotect one of those. These are both the same protecting group. I can protect an aldehyde using an acetal, and that's a slightly different type of protecting group, which would allow me to selectively deprotect when I need to. So let's explore starting with an aldehyde at that position. And then I'm going to protect, or this aldehyde will be protected throughout the major course of this synthesis here. So let's get it protected. Remember, we're still working backwards. And you can see here now that I can selectively deprotect one of these if I need to get here. And then I can turn my aldehyde into an acid, I can turn my acid to acid chloride, and I can make my final product. Now, taking the acetal off using acid and water may actually cause the TMS to fall off too. So if I end up with an alcohol here and an aldehyde here, I could reprotect the alcohol without affecting my aldehyde. So how do I make this compound? This compound is interesting, of course, because it has 2 functional groups. I can use my Grignard reagents to make this secondary alcohol, which then gets protected. And I can make this from maybe an alcohol again. Right, this alcohol could have produced the aldehyde that I used, and now I still have an aldehyde on the other side of my chain. And maybe I have the aldehyde here, and I have this bifunctional compound. So the question really becomes, how do I make this? It has 5 carbons, so I could start with a 5-carbon alcohol, but if I have an alcohol on one side of my 5 carbons or on the other side, I still can't put another functional group on the opposite side. So here's the key to this synthesis that might cause some students pause, but I think once you see it, it will open up quite a few possibilities for you. What if we took this alcohol, cyclopentanol, and we oxidized it to cyclopentanone? And what if we did a Baeyer-Villiger with any peroxy acid to make a 6-membered lactone? We can ring open that lactone using a couple of different options. This is an ester, and so we can attack an ester with either, let's use a different color here just for kicks. We could attack an ester with NaOH. We could attack an ester with H3O+. We could attack an ester with an ethanol and catalytic acid. And we could attack an ester with DIBAH, diisobutyl aluminum hydride. And I'm going to erase these purple things in a while, but let's just see what we could do with this ester. If I use sodium hydroxide to ring open this ester, I will end up with this compound right here, which I could do certain things with synthetic-wise with. If I used acid to hydrolyze the ester, I would get a very similar compound, but I would have my carboxylic acid protonated right off the bat instead of deprotonated. If I did a transesterification, I could get a new ester that has a ring that's opened. And if I used DIBAH, diisobutyl aluminum hydride, remember that can add 1 hydride to esters to produce a aldehyde. And in this case, the other side of the ester gets lost, but it's still attached, so I could make that aldehyde. And look at this. This is actually what my goal was right here. But you could imagine creating this compound, protecting the alcohol, doing some other chemistry on the ester portion of it, and then later on deprotecting the alcohol and getting a bifunctional reagent out of it. You could imagine almost doing the same thing here, protecting the alcohol, turning the acid into a acid chloride, maybe like right up here, and then you could add this to a benzene ring and you'd end up with a pendant alcohol on your chain, which you could do some chemistry with. In fact, that might be easier than what I've been coming up with in my blue pathway. So I would suggest after you're watching this portion of the video, try using this compound created from cyclopentanol as your intermediate to make this compound. And I bet if you protect this alcohol and turn this into a carboxylic acid chloride, you could add this to T-butylbenzene and maybe save a few steps here. But I think I'm going to use this one in this case because this is what I want. I have an aldehyde, I have an alcohol. I can now protect the aldehyde, do some chemistry on the alcohol, then later on deprotect the aldehyde and make my acid chloride. So let me erase the other purple compounds because I don't need them. But I think, I hope that you will consider this as a very simple way of adding bifunctional compounds now, starting with a monofunctional alcohol. And most importantly, providing us with 2 different functional groups, one of which we could selectively protect, and then we could react on the other side. And so in this case, we have the alcohol, and now I can protect that. So let's go ahead and make sure we have the forward synthesis. I'm going to use green here to distinguish everything. So PCC would give me the ketone, MCPBA, would then give me the lactone, and then I can ring open that lactone with 1 hydride using dibol, or DIBAH. That gives me this compound. And my desire then is to take it to here. I can protect that using ethylene glycol and catalytic acid. And then I want to create the aldehyde, so I'm going to use the Swerin oxidation in this case to oxidize the primary alcohol to the aldehyde. I can make my desired Grignard from isopropanol. One step is PBr3. Second step is magnesium. And then, of course, I can take these two, mix them together, follow that up with mild acid workup, and I can make my new bond right there via a Grignard reaction. And then actually the third step would be TMS chloride to protect the alcohol. So now my alcohol is protected. I can remove the acetal protecting group, which requires H2 and H2SO4. And again, if my alcohol protecting group falls off during this step, which it might, I can reprotect it. I haven't lost anything because the TMS chloride would only react with an alcohol. So if I need to, I could follow this step with another TMS chloride to make sure that my alcohol stays protected. Now I've exposed the aldehyde, and I can turn that aldehyde into a carboxylic acid. I could just oxidize this with Jones reagent, or I could use the Baeyer-Villiger, which MCPBA will do the job. And then I can turn the carboxylic acid into the acid chloride with SOCl2 and pyridine. And let's see, so I need to make my benzene ring now. So the tertiary butyl alcohol can make tertiary butyl chloride via SOCl2, turning the OH into the chlorine. I can mix these together in the presence of aluminum trichloride, and I get T-butyl benzene. And then I can mix these two together in the presence of aluminum trichloride, and I get my para-substituted ring. I'll make that bond first. And then second, I need to deprotect. I'm going to use TBAF in this case. And third, I need to take my alcohol and turn it into a bromine. And that would be the synthesis for this molecule. I would like to point out that at this point we could protect this ketone, use this bromine as either an elimination type mechanism or reaction, or a new Grignard formation reaction, and we could extend the chain or add some more functional groups to this if we wanted to. We're going to stop here, of course, because it's quite long, but my point is you could keep going. And you can practice these with your friends just by stringing 10 or 12 reactions together. Being sure that you start with appropriate starting materials, benzene and alcohols 1 to 5 carbons or fewer. I want you to keep this in mind. This ring opening step can help us introduce 2 functional groups when we started with 1, and that can be very valuable in future syntheses. Okay, the second problem here has a alkene formed next to the aromatic ring. It's got an ester on one end of the ring, and we have a meta substitution pattern on the ring. And so at some point we needed a meta director, and maybe we then put a bromine on in the meta position to allow us to make a Grignard in that position, and ultimately make the desired stereo or regiochemistry here. So I'm going to work backwards again. Let me get out my blue. I think probably, but the last step I want to do is to make this ester. Now you might decide that maybe you want to make this alkene as your final step. And that's okay to begin with, but I think we'll find that it's just a little easier to make the ester as our final step. So how do I do that? Well, I need a carboxylic acid here. And I need isopropanol. Catalytic acid will do that just fine. How do I get to the carboxylic acid? Well, I can make the carboxylic acid from the primary alcohol, or I could make it from the aldehyde, then use Baeyer-Villiger, because again, I'm going to have beta positions here that are sensitive to chromium reagents, so I want to be cognizant of that. This may be a 2-step sequence to avoid cleaving off my substituent here. How do I get to this alcohol? Well, I could add 3 carbons, but I don't really know how to get 3 carbons added to the ring with an alcohol on the last carbon. I do know how to add 2 carbons to the ring with an alcohol on the last carbon, or 1 carbon with an alcohol. So let's think about that. I think what I want to do because I suspect that this has to be a carbonyl at some point, which allows me to put a bromine here, which allows me to make this bond via a Grignard eventually. So let's pretend that this 2 carbons came from reacting with that Grignard. So I'm going to add 1 carbon first. And formaldehyde, of course, can come from the oxidation of methanol. And that would require a Grignard here. And that alkene probably came from a Wittig, but let's play with this left side still. This would come from CH3OH, following my rules. This Grignard could come from the ring opening of an epoxide via a Grignard in that position, and ethylene oxide. Ethylene oxide can come from ethylene, can come from ethanol. This Grignard, let's see, I probably can't make that specific Grignard, so I think this, if that's going to be present, that's fine. I can make that Grignard from that compound. I don't have a meta-director yet, but if I envision installing the alkene via a Wittig, now I have a meta-director. And this meta-director, of course, could have directed my bromine to the meta position. This would be plus, let's see, CH3CH double bond PPH3. So I could do the Wittig that way. And I can make the Wittig certainly from ethyl bromide and triphenylphosphine. And I can make this from benzene and the appropriate acid chloride. I can make the acid chloride from pentanol. Oxidation to the carboxylic acid, turn it into the acid chloride. So let's go forward. I'm going to use purple this time. I can do this with H2Cr2O, sorry, I can do that with H2CrO4 and water. That would be the first step. Second step, SOCl2, pyridine. And then, of course, I can react both of these together using aluminum trichloride. Then I can add the bromine via FeBr3 and Br2. I can make the Wittig by reacting that plus triphenylphosphine, and I can make that from ethanol using PBr3. So I can mix these together, and then of course I need to deprotonate my precursor to the Wittig. You can use T-butoxide for that. That's how we get the negative charge on that carbon. Then of course I just mix them together. This is a Wittig. I'll write that down just to remind myself. And you'll see here that that's also a good way to protect this carbonyl. I don't need the carbonyl anymore. It served its purpose of adding the bromine meta, so I could react the carbonyl so that when I make the Grignard here, I don't have any carbonyl that would interfere with my Grignard. So then I need to make the Grignard. That's easy. That's just magnesium. And let's see. Okay, so right here is adding the Grignard to my epoxide, working up the Grignard addition, and turning my primary alcohol into a primary bromide, and turning the primary bromide back into a Wittig. So I've extended the chain by 2 carbons and ended up with a Wittig here. And I can do that via, let's tosylate this and use a really large base. I'm going to make this even larger because ethyl tosylate is a pretty good alkylating agent. So that can do an elimination. MCPBA can give me the epoxide that I need right there. And now I have this vidig can react with formaldehyde. We can mix them together, and we can work them up with acid. And I can make formaldehyde via the Swarn oxidation of methanol. Now I'm at the primary alcohol here. I can create that. I'm going to do that in 2 steps. First step is a Swarn. This might cause some problems, actually. I was going to say, let's do MCPBA here, if I can write it correctly. Do you see where the problem might lie? Certainly the Swarn makes me an aldehyde, and the MCPBA makes my aldehyde into an carboxylic acid. That's not a problem. But I've got this alkene here. And so I really don't want that alkene to turn into an epoxide. I want it to stay as an alkene, and MCPA will react with that. So I need to rethink when I install that alkene, I think. So let's go back and do a little erasing. I'm not going to do the vidig right here. I'm going to protect my carbonyl species. I'll use the vidig later, so I made the vidig reagent. I can still maintain that and use it in a few minutes. But I'm going to protect this carbonyl, and so that means I need to erase all of these here so I can turn them into acetals. And then later on I will remove the acetal, but only after I've done the Baeyer-Villiger. So this acetal can come along as long as I don't add a bunch of acid and water to this. Probably the vidig workups are okay. I don't heat those much, and so this is probably okay. All right, so now I have this primary alcohol under the Swarn conditions with MCPBA. Can you make this carboxylic acid? The acetal should be unaffected by that, and so that allows me then to firstly react my carboxylic acid with isopropanol. So I'm going to do that first. I'm going to actually make another intermediate here. And okay. And then this would go here. So I can erase this, that double arrow there. Okay, so now I can take isopropanol and catalytic acid and make my ester. And then I can deprotect my ketone. In fact, I think I should deprotect the ketone first, which would be this way. So I deprotect the ketone first, and then I make the ester. I can see an issue here. So water and acid will deprotect the ketone, but water and acid would also cause the ester to revert to a carboxylic acid. So it's fine to do it first, deprotect the ketone, but then alcohol and acid makes carboxylic acids into esters, but it would also create an acetal here on my ketone. So I'm not sure there's a way for me to get around this issue, except that maybe I could have my ketone exist in some other form that could then be turned into a ketone. So what if this was a protected alcohol until the last minute, then I deprotected it, gently oxidized it to the ketone, and did the vidig. So that means I would have to erase all of these acetals here and turn them into alcohols that are protected with TMS. And that's pretty easy to do. So how can I get there? Well, I would have to first reduce my ketone and then protect with TMS chloride, and pyridine. And that means that they would all have an O-TMS group in that position, and that's fine. I can remove that later using different reagents than esterification type reagents. And then I can oxidize it gently so that I don't affect the benzylic positions. So let's make this one last one, and then I have just another couple of steps here. And that means I don't need this step here. And that means that should be step number 1, or the only step really. Okay. So I've made my carboxylic acid, I've made my ester. Now the only thing I need to do is expose the ketone in this position and do a Wittig. And so I can do that in the forward direction. TBAF will expose the ketone. Expose the alcohol. And I'm going to try to use the same color here so we are on the same page. So ester, and then I can oxidize, and I would use, let's see here, how would I oxidize that? Probably the Swern. Then I'll get this intermediate, which I will try to squeeze at the top here, if you'll forgive my very small drawings here. I have a ketone, and now I am one step away from my product using the Wittig. And I'm not going to draw it here, but we have the Wittig down here. So we've already made the Wittig reagent. We can use that at the last step to react with this ketone to make the alkene here next to the ring. And so you see in this case, it took me a few iterations to work my way through this synthetic process. And that's fine if that happens to you. This is a learning process. So we'll try one pathway. We might find a drawback. We may have to go back and fix our pathway a little bit to get to a place where we can avoid that drawback. And you saw in this case that it took me 2 iterations to get there. So if you're having struggles or you're having to revamp your synthesis pathway, that's fine. That happens to everybody. Don't be discouraged by that. All right, one final synthetic example using carboxylic acid derivatives. And we see here that there's a 6-membered ring, cyclohexane ring, that has 2 substituents on it. And that, I think, is the challenge with this problem. How do I get 2 substituents on that cyclohexane ring when I can only start with cyclohexanol if I choose, or I can't even start with cyclohexanol. Remember, I can start with benzene and alcohols of 1 to 5 carbons. However, remember that benzene can be reduced fully to make cyclohexane. And if this were a benzene, this is now sort of a meta-substituted benzene. So what if the final step, or one of the final steps, was reduction of benzene that already had our groups in the meta position? I could reduce this fully. Actually, I don't think the carboxylic acid would survive the reduction, so I probably would want to maybe start with an alcohol. And if I reduced it, then I could just oxidize the alcohol at the end, and I would have my product. The next question is, how do I get to this meta substitution? This appears to be a Friedel-Crafts acylation, but remember that those don't work on moderately deactivated rings, which is what I need if I had a meta director. I could make this bond right here, that bond, via a Grignard, and then eliminate or reduce fully the resulting alcohol. So maybe that's an option. And this, of course, doesn't have to be an alcohol. This alcohol is a orthopara director probably because it's an electron donating group. It's a carbon here. But if this were an ester or an aldehyde or a ketone, that would be a meta director, which would allow me to make a Grignard at this position to make that bond. So let's work backwards here. If I had the aldehyde, now I have a meta director. And if I had that bromine there, I could protect my meta director or change my aldehyde so that it wouldn't react with Grignards, make a Grignard, add the 3-carbon chain on the bottom. And so I can get to this bromine, of course, from benzaldehyde. And now the challenge is to make benzaldehyde. We know a couple of options. We could add phenyl Grignard and the 1-carbon aldehyde, and then oxidize it once more to the aldehyde. Another option would be to use ozonolysis on vinyl benzene. All right, I could use ozonolysis and cleave that, and I could make vinyl benzene from ethyl benzene through the bromination of ethyl benzene. And I can make ethyl benzene, of course, from ethyl chloride and benzene. So I'm not going to show you, I'm not going to complete that retrosynthetic pathway. I think I'm going to use the blue one because it's a little shorter, but you're welcome to use whatever you wish. So let's start working forwards. I can make formaldehyde from the Swern oxidation of methanol. I can make phenyl Grignard from, let's see, Br2, FeBr3, and second step would be magnesium. I can mix both of these together and I can make this compound. That's not a meta-director though, so I can oxidize that. Let's use bleach in this case, just because it's fun and green, greener than the Swern or the PCC type reagents. Now I have a meta-director, and I can add the bromine meta using Br2 FeBr3. And I'm going to branch off here again. I can take this now, and I think I'm going to reduce the aldehyde to the alcohol and then protect it. So I'm going to use NaBH4 to reduce the alcohol. I'm sorry, the aldehyde. I'll do that in ethanol. And then I'm going to protect the alcohol, TMS chloride, in pyridine. And I need to protect it, of course, because my goal is to make a Grignard. So I have the bromine here. Now I have my protected alcohol. And if this alcohol is protected all the way up to basically right before here, I can deprotect it, fully oxidize it to the carboxylic acid. So that's pretty much my carboxylic acid. I just need to install my alkyl group here. So I can do that with magnesium, and then I need to add a 3-carbon chain in the middle, so I'm going to use acetone, and I'm going to follow that up with mild acid workup. That'll give me this. And I'm afraid I'm running out of room in this upper right corner, so if you'll forgive me, I'm going to keep branching to the other side. So now my goal is to turn this compound into this compound. And I can do that by eliminating this OH, and then I'll be ready to reduce to the cyclohexane ring. So to eliminate that OH, I can use TMS chloride to make it into a better leaving group. That goes with pyridine, of course. And then I'm going to use a large bulky base just to make sure there's no substitution or anything. And that would give me the alkene. And I can reduce the alkene, of course. But here's a nifty thought. This alkene would get reduced at the same time that the benzene's reduced, because remember, it takes really forcing conditions to reduce the benzene. So if I'm going to reduce benzene, that alkene will get reduced as well. So let's just do that all at once. This takes hydrogen, palladium, and 300 atmospheres of pressure. So we use a lot of hydrogen, and we can reduce basically anything that's reducible, including the alkene outside the ring and the alkene in the ring. And then I think I'm about 2 steps away from my product. I can deprotect, and then I'm going to oxidize to the carboxylic acid using Jones reagent, H2CrO4 and H2O. So I deprotect to make the primary alcohol, and the primary alcohol then gets oxidized straight to the carboxylic acid. And This, of course, is the same as my target up here. I just didn't get there using my... I didn't get there logistically on my paper because I ran out of space. But these are the same, and so now I've made this this target from basically benzene and acetone and a couple of additions of, or one addition of formaldehyde. And of course, you could have made it from ethyl benzene if you wanted to. You could get to this aldehyde from a different route. So really, whatever you want to do is fine. No one route is the perfect answer. If your route is correct and doesn't have any places where you might react with something else on your molecule or make a different reaction that you weren't intending to, or perhaps get a 50-50 mixture of products, your route probably will work just fine. And you're welcome to bring your proposed routes to my attention in person or via picture in an email, and I'd be happy to assess them for you.